This is Josh White with JW Math Tutoring. In today's video, I'm going to cover 3 more advanced use cases of regression to solve some of the digital SAT Math's hardest problems. So let's go ahead and get right to it.
But life is a dream that calculus could never predict.
Welcome back to my ultimate Desmos guide to digital SAT Math. In this video, I'm going to go through basically 3 more advanced use cases of regression. Now, a couple things to keep in mind just before we get started. First, for the problems that I go over today, which are part of my overall Ultimate Desmos Guide to Digital SAT Math Practice Problems worksheet, there'll be a link in the description and also in the pinned comment below for just these 6 problems. There'll also be a link to the entire list of now 58 total problems. So you can download either the whole thing or just these 6 problems if you've already looked at the previous videos in my guide. Related to that, if you haven't done so already, please check out the other parts of my Ultimate Desmos Guide to Digital SAT Math. I've got the core skills, intermediate skills, multiple videos on advanced skills, and basically advanced use cases of regression. So if you haven't looked at those, if you haven't done the practice problems related to those, please do check those out as well. And lastly, of course, if you like this video, please give it a thumbs up, subscribe to my channel, and sign up for notifications. All right, so let's go ahead and get started now with the first, I don't know what to call use case, or on the worksheet you see here, first topic. And oh, sorry, one other thing. There'll be a link to the description and the pinned comment, of course, for this operations guide. Basically the PDF file that has what you're seeing on the left side of your screen right now. Okay, so basically the type of problem that we're going to solve here is finding the value of a constant in a quadratic expression given that the expression, or really the equation, has one solution. All right, so what we're going to do is essentially take the original problem, make sure that it is set equal to 0, so that might mean moving some terms around from one side to the other, and then we're going to do regression, and essentially what we're going to do is we're going to regress this quadratic expression to its vertex form, except we're going to make the k value, which is the y-coordinate of the vertex, be equal to 0. And doing that, we'll find the value of the constant that gives this quadratic expression only one solution, because the vertex of the quadratic, which you'll see from the graph, will now be on basically the x-axis. It'll be something comma 0. All right, so and of course, as part of this, we're going to have to define a list for x1 because we want Desmos to treat that as a variable, not as a constant. All right, so let's look at some example problems to show you exactly what I'm talking about. All right, so here's the first example from the guide, problem 53. Here's an equation, okay, and basically it says the following equation has exactly one solution, find the value of c. So in other words, what's the value of c, which is a constant, such that this equation has only one real solution? Okay, so what we need to do first is you basically need to get everything on one side equal to 0. So the easiest way to do that would just be to subtract over the 10x and subtract over the 4c. So then you would get 2x squared minus 5x minus 10x plus 7c minus 4c. Now, you do not need to simplify this. You can just enter it in as it is. You don't need to make it negative 15x. You don't need to make it 3c, and I'll just show you that when we go through the problem here. Of course, because I'm doing regression, I'm going to type in x1, not just x. And I'm just going to type, again, everything here on the left side of this equation because it's equal to 0. Now I'm going to do regression, and I'm going to regress it to its vertex form. Now, the vertex form would typically, again, look like this. However, I'm not going to do this because I want the k value to equal 0. So I'm just going to get rid of the plus k essentially just telling, Desmos to let the k value equal 0. All right, so now we have a c value. However, this is not the correct c value. The reason is because it's treating x1 as a constant, not as a variable. So we need to define a list for x1. So now we can go ahead and do that. Let's just put in some numbers here. Okay, and notice once I get a couple values in there, now it does give me essentially the correct values for A and for C and for H. So C is going to be 9.375, or as a fraction, it's 75 over 8. Okay, so the correct answer for this problem is either 75 over 8 or 9.375. And now just to show you, for example, if you typed out, I'm going to graph the left side. Okay, notice it carries the value of c over. Okay, so I'm just typing y equals the left side, that's what I have. Notice if I type y equals, and now if I type the right side, which is the vertex form, notice they are identical, right? I click this off, I see the purple. Click this, nothing, it's completely hidden underneath it, that's why nothing changes. So this just confirms that I have found the correct value of c such that this expression has one real solution because there is one x-intercept for the graph of this quadratic, which we can clearly see on the screen right here at 3.75, comma 0. Okay, so let's look at the next problem now, 54. So for this one, we're going to use the same basic approach. And let me just jump back to the worksheet here. So under the notes section, the last thing listed here, it says, note, this can be used in non-quadratic equations if they can be turned into a quadratic by squaring both sides. So what we're going to do here is we have this k minus x problem, very common advanced problem that you see in Module 2 towards the end a lot. And this is not a quadratic as it's given. However, you can do a little work and you can square both sides. Okay, and so on the left side, root k minus x quantity squared is just k minus x. On the right side, you can just leave it like this. You do not need to FOIL it out. You do not need to simplify it. Now we have a quadratic equation. So now I can go through the exact same steps, the exact same process for this problem to find the minimum value of 4k such that this equation has one real solution. Same exact conditions as the previous problem. So you do need to get everything equal to 0. It doesn't matter which side you move everything over to. I'm going to, I guess, probably move everything over to the left. So this work also, I mean, if you can do this in your head, that's fine. You don't need to write this out, but if you want to, that's fine as well. So now I'm going to enter in the regression statement. Of course, I need to remember to make all my x's into x1s. Okay, so now this is going to be regressed again against the vertex form, and specifically the vertex form where k is equal to 0. Now, not to be confused, here, this already has a k in it. That's a different k. That's not the same k as the y-coordinate of the vertex, which again, normally, would be right here. But again, I'm not including that. I'm forcing that to be 0 for the vertex form equation of this quadratic. All right, so now, again, we need an x1 list because we want Desmos to treat x1 as a variable, not as a constant. So let's just do the same thing we did on the last one. Okay, here we have the values of k, a, and h. We're really only concerned with 4k. So we can just type in 4k here, and we can get 75. And that's our answer. That is the minimum value of 4k. That is how to do this entire problem, basically in Desmos, except for maybe, writing out a step or two that you see here at the beginning. All right, so that is the first advanced use case. Let's talk about the second one, which is similar to this or related to this. It's a different type of problem, but the overall approach is basically going to be the same, at least for the first method. There's actually two methods, though. So these are for this advanced use cases for problems where You're given basically two functions, typically a quadratic and a linear, and you're told to find the value of a constant such that they intersect one time. Okay? There's going to be two different methods you can do on this. The first method is to set basically the two functions equal to each other, then move everything over to one side to get it equal to 0, just like we did in the last problems, and then do regression to the vertex form, again with a y-coordinate of the vertex equal to 0, basically the same exact process that I was just doing on the last two example problems, okay? The second method, I'll talk about that in a second. I just want to show the first method and go through that, and then I'll talk about the second method, which technically uses derivatives. So let's go back to the problems. Let's look at this example, number 55. Here we have a quadratic, and we have a linear function, and they intersect at one point. That's what we're told. We want to find the value of c such that that's true. Okay. So you might have to do a little work by hand here because you need to basically get these equal to each other. So the first one, is just going to be this minus c, and the second one, if you add c to move it over, you're going to get this. Okay, then you set these two equal. So you would have x squared plus 14x minus 5 minus c equals negative 2x plus 4 plus c. Now you need to get everything equal to 0, so I'm going to move everything over to the left. Again, you do not need to combine the terms, so I'm going to add 2x to cancel this. I'm going to subtract 4 to cancel this, minus 5 minus 4, and I'm going to subtract c to cancel this. And again, I said you don't need to combine the terms, so I will just leave them separate. Again, if you can do this in your head, you can move everything over, that's fine. You could also just like take this original thing and just put a giant minus behind it if you want to think about it that way in terms of moving the expressions over. All right, so now I got this whole long thing to type in. And I'm going to do regression to the vertex form, but with a y-coordinate, i.e. a k value equal to 0. Okay, so it's given me a value of c. Again, that is not the correct value of c because it's treating x1 as a constant, so I need to do my list for x1. All right, so now once I've entered in a bunch of values, here is the correct value for c, negative 36.5. That is the correct answer here. And let's just go ahead and graph this out and confirm that when I graph each of these two equations, let's get rid of this just so I have the originals here. So we have y plus c. It should carry the value of c over. Okay, so there's my original. There's my quadratic. Let me zoom out. And then for the second one, okay, so notice we can see here nicely on the graph there is one intersection point. Where is the intersection point? It looks like it's somewhere maybe at negative 8, negative 16.5, somewhere right around in there, but we're not necessarily concerned with that for this problem because we only want the c value. That's all that we're asked to find. All right, so now let's go ahead. Let's talk about the second method or the second approach. This basically uses calculus and uses derivatives, and I'm going to keep the graph up on the screen here just for a second before I actually go through and type everything in. So basically what you're going to do is you're going to type each function in as f of x equals and g of x equals. That means that you technically need to get y equals and move any other terms that are on the same side as the y to the other side of the equation first. Okay? Once you've done that, then you're going to type what you see listed in step 2, which is basically a system of equations that is being solved using regression. And essentially what you're regressing is f of x to g of x, which those are the original functions themselves. Those are their y values. So in other words, it's telling you to set the y values equal to each other. then you're also technically regressing f prime of x and g prime of x. Okay? That's the derivative of each of those functions. If you have not taken calculus and you don't know what a derivative is, don't worry about it. You'll learn about it later. Just memorize what you have to type in. The derivative is essentially the slope of the tangent line at a given point. So really what this system of equations is doing, what it's telling Desmos to do is, it's saying, okay, I want you to find the point where both functions have the same y value, same y coordinate, and the slope of the tangent line, i.e. the value of the derivative, is also the same. And that will give you the value of c, or whatever constant it is, such that the two things intersect once. Okay? So again, if you don't understand the theory behind this, that's fine. Just memorize what to type in and how it works in order to use this method. One other thing, too, is this method will graph both functions as part of the process. So it's a little bit better than the first method in that the first method solves for c, but the graph itself is not provided. I had to do that myself. So let's go back to the problem now. Okay, and again, both of them need to be entered in of the form f of x equals and g of x equals. That means it needs to be y equals on one side. So we have to do, what I did originally, which is just put a minus c here and put a plus c here. And then I'm going to graph the top one as f of x and the bottom one as g of x. Okay, and now, again, I'm going to type in a system of equations. I want f of x, comma, f prime of x, and then regression, and then f of x is being set equal to g of x, i.e. we want them to have the same y coordinate, and f prime of x is being set equal to g prime of x. We want them to have the same tangent line slope of their derivative. Okay, so, sorry, here's the mistake. Notice, it's not giving me anything, it's not returning anything, right? That's because I didn't use x1 in my regression statement. That's the problem. So if you click on this, x may not be used. Okay, so if we change this to x1, then what you're going to notice, there we go. Notice we get the value of c. Notice we also get the value for x1. And x1 right here is technically the intersection point. That's the x-coordinate of basically where the line intersects the quadratic or the parabola at one point. Now we don't need that again for this question. All we need is the c value, which is negative 36.5, but now we have the value and we have a nice graph. So again, this method will show you how to do this problem using this method will show you how to do this problem and get the graphs. You can just visually confirm, that everything is correct. All right, so let's go ahead and take a look at just another example to practice. So for this one, I'm just going to use the second method since I think it's a little quicker, a little easier just to get practice with that. So minus c plus c. But you can feel free to go ahead and use the first method if you want. So there's the first function. Here's the second function, f of x, f prime of x. Remember to use x1. Regression, g of x1, g prime of x1. Okay, and here we have the value of c, which is 2.375 or 19 over 8. So the correct answer for this, 2.375, or as a fraction, 19 over 8. And also here, the x1 is 4.5, and you can just see here, yes, it's at 4.5, 4.5. That is basically the x value for the intersection point where these two graphs intersect one time. All right, so let's talk about the third use case now. This is basically finding the value of a constant or one constant or two constants for a system of equations to have infinite solutions. So this is basically an alternate method to a use case that I covered previously in a previous video. In the previous video, I was showing how to use regression to find the value of one constant. But this is an alternate method you could use if you only need to find the value of one constant, or this is a method you can also use to if you want to find the value of two constants. Okay, so let's say there's like a C and an A or an R and a P or whatever it is. Okay, so this will work for that as well. Basically what you're going to do is you're going to take each equation, you have to move all the terms to one side so that they're both y equals. All right, and then all you're going to do is you're basically just going to do regression to set those two equations equal to each other, and then that's going to find the values of the constants, C or A, R, P, Q, whatever it is, such that those lines are equal, because if you want this system of equations to have infinite solutions, that means both lines are the same line. Now, when you move the terms over, you don't have to combine them. You don't have to simplify them. You can just use one gigantic expression with multiple terms for the x or the the numbers or whatever. But you do need to remember to use x1, of course, as we set up the regression statement. So now let's go back to the problems. Let's look at number 57 here. Okay, here's a system of equations. It has infinite solutions, you're told, and you're asked to find the value of c over a. Okay, so there's a c here, there's an a at the bottom here. You need to solve each of these for y. So that does require a little bit of work. So in this first case, basically you would do minus 1/2 x, and then just multiply everything by 3. Okay, the 3 will cancel out the 1/3, and you can just leave it in like that. So on the left side, I'm just going to type 3 and then parentheses 1/6 minus 1/2 x1. Okay, now on the bottom one, basically what we have to do is minus 1 over ax. That'll cancel out that. By the way, x should be on the top here. Okay, and then this one's a little tricky. You have to basically multiply by the reciprocal, 2c over 3. So this entire thing, you're going to put a 2c over 3. Again, if you can do that in your head, perfectly fine. So I'm going to put 2c over 3, and then the giant parentheses, and then I have 2 minus 1 over a x1. Okay, now it's giving me values for a and c. These are not the correct values, I don't believe, because it's returning value for x1. So let's do a list for x1, because we want it to treat as a constant. Okay, so now these are the correct values for c and a. So what is the value of c over a? It is 2.25, or 9 over 4. Just click the fraction button. There we go. So either of those would be acceptable as correct answers. And again, just to confirm that we have the right solution, what I'm going to do is I'm just going to graph each of these lines, and we'll hopefully see they are the same line. It's 3 over 2c y equals, so let's see, when this line shows up, notice it completely overlaps it. Notice that same line, infinite solutions, that confirms our values of c and our values of a are correct. Click this. Yep, same line. Okay. So let's take a look at one more example problem down here, number 58. So again, same thing, you have to get everything in terms of y equals. So it does require a little bit of work on the front end. So you could do minus 1/2 x here, and then again times 3. So the first thing is just going to be, and again, I'm only entering in the right side. I'm getting y equals and then everything else on the right side. So there's a 3 and then an r minus 2/3 x1. minus a 1/2 x1. All right, and then for the bottom one, let's see, I need to minus 1 over px, 1 over px, okay, so that's gone, and then multiply by 2/3. So we've got 2/3, and then times 3/4 minus 1 over p x1. Okay, now again we need the list for x1. Let's just try doing this as a shortcut way to get 1 through 5. All right, let's see what r over p is equal to. Looks like 0.875, or as a fraction, 7/8. So the correct answer to this one is 0.875, or again as a fraction, 7 over 8. You could also technically type in 0.875 as well. This was a free response question. So again, let's just confirm that we have the correct answers. So just erase this so I can see the original problem nice and clearly. X plus 1/3 y equals r minus 2/3 x. Okay, there's our line. Let's look at our second line. Y equals 3 over 4. I forgot the x. That's why it's giving me a horizontal line. Okay, there we go. Notice, again, infinite solutions, same line on top of itself. That just confirms we have the correct answer. All right, so hope you enjoyed this video going through some more advanced use cases of regression to solve some of the hardest problems on the digital SAT math section. If you did like this video, please do give it a thumbs up, subscribe to my channel, and sign up for notifications. If you have any questions or comments, please leave them below. And as I mentioned, if you have not done so, please check out the other, I think there's technically 9 other parts of my Ultimate Desmos Guide to Digital SAT Math. And check out the rest of the practice problems if you haven't done those yet. But otherwise, good luck in your preparation for mastering Desmos to score as high as possible on the digital SAT Math section as you can.